Ready to start? Okay. Hello, everyone. Welcome to HackGPT. Give yourselves a round of applause for showing up. Woo-hoo! Okay, sorry about the delayed start, but we're going to go ahead and get started. So welcome to HackGPT. This is a beginner to intermediate level workshop that's on integrating AI into your personal project. So, hello. Before we start, here are the slides in the GitHub if you want to follow along. We're going to be doing 2 separate demos today, and that you can find those on the GitHub, and then also the slides, which have very detailed how to set up the environments and also work on pretty much anything you need to know for this specific event. Okay, before we get started, we'll do a little team introductions. My name is Lorelei.
Kian.
And we are your HackGPT directors. We're going to be putting all this together, but we couldn't have done it without the help of our team. So our curriculum team, sitting over there, you guys can introduce yourselves. Yeah, and they're going to be presenting the demos later on in this workshop. And then we also got our marketing and support teams, which are probably the people that got you here. You guys can say hi in the order that you are here. And then Max is back there. Yeah, and then we got Kayla and Nathan coming with boba and portos for you guys. Okay, so here's a little agenda overview. So this event is actually going to be split into 2 parts. We're going to have part 1, which is a technical workshop, and then part 2, which is the interactive work session. So what's going to happen is for the very first 2 hours, because this is a 4-hour event, we're going to give you everything you need to know to basically build your own project. We're going to go over AI and APIs as a general concept, and then we're going to go through 2 in-depth demos. One is going to be RAG, and one is going to be multi-agent network. If you don't know what those are, that's completely fine because we're going to go through what those are very specifically in the later half of this workshop. And then for the second part, it's going to be an interactive work session where you guys are going to pair up and you're going to pick one of those demos to base your own project off of, and you're going to have 2 hours to work on that, and the best projects will get prizes. Just as a little disclaimer, some parts of this workshop are intended to be follow along, like the first demo, while the second part is not as follow along. But don't worry if you get lost because you'll have access to the GitHub and the slides. If you need it, we can send it back out while you work. Yeah, does anybody have any questions about how this is going to work? So the end goal of this workshop is to integrate your own AI API into your own personal project. And the best final projects by the end, by like 5 p.m., are going to win special prizes. We got like chargers, adapters, anything else that might be interesting, like a holder for your cables. It'll be super cool. Plus, we'll have snacks. Okay. Okay, so we're going to get started with the first part of the workshop. Can anybody give me an example of AI? If you answer, you get also free squishies. Sure, go for it. What's your name? Thomas? Hi, Thomas. What'd you say? Yes, ChatGPT is a great example of AI, but in a more theme sense, because our theme is Wally and Eve. Wally and Eve are essentially AIs, or artificial intelligence. They're curious and intelligent robots that are capable of learning, understanding, and making decisions. Just like how Wally and Eve are curious about the world and they'll explore and collect information to make decisions and learn more about stuff, AI does the same thing. It processes data, learns patterns, and generates intelligent insights so that it can produce more relevant outputs for whatever use it has. Okay, no, but seriously, what is AI?
Okay. I'm just going to give you guys a quick, broad overview of what is artificial intelligence. So AI is basically just a computer and its ability to perform tasks that typically require human intelligence. A quick example of that is you guys probably already know what an algorithm is. It's just something that takes an input and performs like a set operations on it and has an output. So for example, if you gave an algorithm, what is 70 degrees Fahrenheit in Celsius? It would perform these set operations and it would output 21.1 degrees Celsius. But you probably know that, like, as a human, if I was to ask you something like, oh, what's the weather going to be tomorrow? You don't really have an algorithm in your head. It's more just like using things like your memories, your experiences, your intuitions. And you might say something like, oh, probably around 70 degrees and it might rain in the afternoon. And AI was built to mimic human thought. So similarly, when you ask an artificial intelligence, how will the weather be tomorrow? It will use similar things, not the human memories, experiences, intuitions, but rather its data sets, its pattern recognition, and its understanding of probability to output something like, tomorrow, May 19th, 2025, LA is expected to experience cool temperatures and so on. And yeah, there's many different types of AI. We're gonna be focusing on three different ones just for this session. The first one is machine learning, which broadly is just how computers learn from data without being explicitly programmed, like I said, in those algorithms. This involves training algorithms and on data sets so they can recognize patterns and make decisions. The second is natural language processing. Like you said, ChatGPT is a great example of NLP, and that's just how computers understand, interpret, and generate new human language. They power applications like chatbots, sentiment analysis, and things like that. And lastly is computer vision, which is kind of similar to ChatGPT, but instead it's working on images rather than text. Examples of these three different types of AI. For machine learning, you can maybe build an app that predicts house prices or detects spam in emails. For natural language processing, like we said, ChatGPT, also Google Translate is a great example of natural language processing. Computer vision, the Google Vision API, if you guys ever heard that, it's just something that you give it images and it can detect what's there. And also autonomous vehicles like Tesla or Waymo, if you guys have any experience with that, is a good example of computer vision.
So now that we've talked a little bit about AI or artificial intelligence, let's talk about APIs, which are going to be the central focus of today's workshop. Can anybody tell me what API stands for? It's okay if you don't. Yes? Yes, ding, 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 that's exactly right. Application Programming Interface. But what exactly does that mean? So an API is basically a messenger or a translator that allows different softwares to talk to each other and exchange data. It basically provides a set of rules or protocol to allow different applications to send information to each other, send back responses, send requests. It sort of acts as a communication platform between different applications or software platforms. So why are APIs relevant for our use of AI? Well, why do work when someone else can do it for you? The thing about AI is that it's very complicated and very complex to build from the ground up. But what's good for us in the generation that we live in is that a lot of AI has already been developed. So for example, ChatGPT or Google Gemini, those have already developed multiple different useful uses of AI. And so we can use those through the use of APIs without building them from scratch. And the benefits is that, it's easily accessible. So they're pre-trained models. You don't have to train them yourself. They're scalable, so you can use only which part of it that you need. And they're time saving, so you can skip all the model training. Basically, these big companies have already done all the work for you, so we're just going to utilize that to put into our own projects. And that's what we're going to be doing in this workshop. So some real world examples of AIs in real life applications. Chatbots, if you've ever been to like a marketing site and you see the little chatbot in the corner, that's probably using some sort of AI API. Image recognition, like Kian was mentioning earlier, that detects objects and images. The Google Vision API, if you've ever scrolled through your photos and it tells you what the photo is, that's an example of an AI API. Same thing with language translation and other examples, like the very first AI overview you get from your Google search. So some popular APIs, there's lots of different options. I'm not going to read through them all, but you guys have access to these slides, so you can look over these later. There's text processing, speech to text, text to speech, image recognition, custom models, tons of fun stuff to play around with that already exists that you can find creative ways to integrate into your own project to create more use cases for. So how do we use these together? Basically where the magic comes in is we're going to be using endpoints, authentication, and a request response cycle. So endpoints are basically points in your code or from the server side or whatever's providing you the information where the URL for the API is going to receive requests. It's going to pass that information through an authenticated token or API key of some sort, and then that's going to set a response cycle. So then once you send information to the API, it's going to process it, it's going to come back, and that does it over and over again until you have a working project.
Okay. Now that you know a little bit about APIs and also AIs, I'm going to be telling you guys a little bit about how you can integrate these two together. So you might be questioning like, oh, how am I supposed to use AI in my project if ChatGPT is kind of just like a chat box? And that's a great question. I remember I was thinking that when I first got into like AI. What the API lets you do is essentially you can use the input and output of like a ChatGPT request as like strings or variables in your program. So you can have a variable, you can give it to ChatGPT, and then you can use the output in your program. A good example of this, let me just a very basic, just simple example is like, let's say I want to make a recipe suggestion app. and I prompt the user, oh, like, what do you want to eat today and what do you have? And they'd say something like, oh, I have tomatoes, cheese, and bread, and I'm craving something Italian. And you'd use that as an input into the ChatGPT prompt. And you might append it with something like, oh, please tell me what I can make with these ingredients and with these preferences. And ChatGPT would give you your output and you would just print that output into wherever. And it would say something like, oh, you should make a cheese pizza. Here's the recipe. Obviously, this is not that useful. It's not that great. We'll be making a lot more fun projects and better stuff in the demos that you'll see. But before we get into that, I want to give you guys kind of two useful things to know. The first has to do with API keys. So when you're interacting with ChatGPT or any other generative AI through APIs, they don't just let you do it however you want. You can't just send a request willy-nilly, basically. They put a lock, kind of like metaphorically, on who can access their APIs, and you can pass through that lock with what's called a key or an API key. I'm gonna walk you guys through how to make that so you can access your generative AI in your own programs. For these demos, we're gonna be using Google Gemini instead of OpenAI because they offer free API keys, whereas OpenAI has like rate limits and you have to pay for it. So yeah, you want to start by going to aistudio.google.com. It'll look something like that. Yeah. If anyone wants me to slow down on this part, please let me know. And then you're gonna click this top right part that says get API key. And so somewhere in this process, you might have to log into a Google account somewhere just so you can have an account to work with. That'll take you to a screen that kind of looks like this. From there, you can this kind of gives you a quick start on how you can use the API in your terminal. You don't really have to worry about that. In this top right part, you can click create API key. And then from there, it'll give you your own API key. I blurred mine out so you guys don't have to use mine, just use your own. And you want to copy it and just store it anywhere, maybe in like a notes app or just like a scratch pad, just so you can use it later and you don't have to go back and do this again. So yeah, that's your very own API key that lets the Google or Gemini know that you're the one making these requests when you're doing the API call. A good thing to know is API key safety. A lot of times when you're programming, you're going to want to upload your code to GitHub or post it somewhere where people can see your code through repositories. And what happens is if you just put your API key inside of your code, people, sorry, this is an example of like a GitHub repo, like our demos and stuff are all hosted on GitHub. So yeah, if you were to put your code or your API key hard coded into your code and just put that on GitHub, anyone can see your API key and they could use that to make calls through your account. And like right now, we're only using free API calls, but if it was paid, like they could just theoretically charge your credit card for whatever. So instead of doing that, we're not going to get too deep into this. You guys probably don't have to worry about this right now, but it's good to know. You'd make something that's called an .env file, which stands for environment variables. And instead of having the API key hard coded into your actual like JavaScript file, you'd use the variable that's already in your environment variable, and you wouldn't push that to your GitHub. So it wouldn't be online anywhere, essentially. You guys probably don't have to do this for this demo, but it's just good to know. Another good tip is to keep up with the demos. There is a lot of code involved, so I wouldn't suggest trying to code it all yourself, but I think it'd be good to have it on your computer so you can follow along. If you want, go to this link or just scan the QR code somehow. You probably want it on your computer, so I'd suggest actually going to the GitHub. And then on your terminal, you can just write git clone and the link to the GitHub. And what that's going to do is it's going to copy all the code and all the folders from our GitHub into your computer. I'll let you guys do that for a sec. And it's going to be wherever like your root folder is if you just type that in. So it's usually just like, yeah. And then from there, you can just find it in your like your folders and go there and open it in like VS Code or whatever you guys want.
And we know we're going through this kind of fast, but it's because this whole segment's going to be 2 hours long. So we want to make sure that you guys have all the tools you need for the 2-hour work session so that you guys can build this. But keep in mind, all of this is on the slide. So if you ever get lost during the work session, we'll be going around to you if you need any help setting this up. So don't worry if it's confusing or anything like that. We're here to help.
Yeah. Anyone wants me to slow down, or is everyone good with the git clone and cloning the GitHub repository? Okay, and then from there, yeah, that should show up. You can just open it. I personally use VS Code. You can use whatever code editor you want. You could open it inside VS Code and you should have something like that. That's all the code we're going to be working with in the demos. So yeah, without further ado, it's demo time.
If you guys have any questions, we'll be walking around. And you guys can ask us for help with setting up the environment variables, but yeah, we're just gonna go through the demo.
All right, hi guys, my name is Jeff. I'm gonna be going over like an overview of what RAG is. Here we have a link for our first demo. I'm just gonna give a description of how RAG works and some simple code. You can copy that link into your computer to first look at like our demo, but I'm just gonna be going over an overview. So firstly, does someone know what RAG stands for? No? All right. So RAG stands for Retrieval Augmented Generation. And it builds on a LLM's pre-trained data. But LLM is basically a large language model. What that is like what you imagine OpenAI or like Google Gemini to be. It like you speak to it or you can talk to it and it'll give you a response back. And it allows the user to input their own knowledge base without retraining the model. So what this means is that an LLM is already pre-trained on a set of data. And let's say you have your own data that you want to train the LLM on. A RAG system allows you to do that without actually having to retrain the whole model. So it's much faster and you can like produce your own results. And it combines retrieval, which is basically getting your own data with generation into the LLM to produce enhanced responses. So how it works. So firstly, you would obviously need your own data. You would enter raw data into your pipeline and you will use this in a later step. So for step 2, what you need to do is to ensure that the document can fit inside the token limit of GPT or Gemini. What a token limit is basically large language models have a certain size that you can only input to it, because if you input so much data, it takes up too much memory and it's very inefficient for the data to process. So you would need to split up your document first and then feed it into the LLM later. Basically, it just costs too much money for the LLM if you input too much data. So they require token limits. For part 3, you would need to store it into a vector store. What a vector store is that it stores vector embeddings. What this means is that you need to turn in your take your raw data and then turn it into vectors so that your retriever, which we'll go over in the next step, can retrieve that data and feed it into the LLM. And what a vector database is it stores and retrieves vector embeddings based on their similarity. So vectors are basically numerical representations of your raw data. And then for part 4, the relevant bits are taken from the storage along with the user input. So basically, you would ask a question and your retriever would take the relevant vectors from your vector store along with that question, and it'll create a prompt. And then this pipeline generates a prompt using the retrieved data and your user input, and it will feed it into the LLM to create an answer for you. So chains are a very important part in RAG. I'll go over what that means. It refers to the number of operations that allow you to retrieve and generate your final your final answer. So it's basically just this diagram over here. That's the chain. Lane chain and llama index allow you to chain components. But what are lane chain and llama index? So these two frameworks are the two main frameworks for building LLM-powered apps. It makes it easier to build chatbots, search engines, and document Q&As. Later in our demo, we're going to be going over how to input a Wally script into a RAG system. It supports integration with technologies like OpenAI, BERT, and Google Gemini. What's the difference between llama index and lane chain? Lane chain allows for more granular control over each component of your workflow. So like you can change your different retrievers. So that's what takes it from the vector store. And LLMs like OpenAI or Google Gemini or BERT. LaneChain is better at building complex pipelines into a multimodal RAG system. So this sounds complicated, but it's pretty simple. Multimodal just means different types of inputs, like images, videos, text, or like speech. And it's basically easier to just change different components of your RAG system using LaneChain. For Llama Index, it has a simpler implementation and it's more efficient for smaller scopes. So if you want to build something quick and simple, I think Llama Index will be a better choice. Here's a chart to show the differences between Llama Index and LaneChain. You can look over it later if you want, but basically the main difference is that LaneChain just allows for more complex pipelines. So here's some sample code on how to load a document into Llama Index and LaneChain. Just be aware that these two are like separate frameworks and you can choose either one. But for our demo, we'll be using LaneChain. For Llama Index, you would import a simple directory reader and just it will load your document into a variable. For LaneChain, it's basically the same process. You would import a text loader and load your document that way. Okay, so the next step would be to split up your document so it can fit within the token limit of your LLM. For Llama Index, you would import a token text splitter, and then you need to specify your chunk size. So that's the number of sizes you want your splits to be. Here I specify it to be 1,000 tokens. That's basically just the word size. For LaneChain, you would import a character text splitter, and here we need a chunk overlap. Llama Index automatically does that for you, but for LaneChain, you have to manually do it. So what a chunk overlap is that for an LLM, you need it needs to have context for each split. So you want your splits to overlap with each other so that your LLM can have context. And then it's basically the same process though. Okay, so I know you guys are all tired. It's time for a brain break. Do you guys have any questions about how RAG works? No? All right. Here's a little animation that I made. Yeah. All right. Hopefully you guys are ready to process more information. All right. So now you'll need to index your splits. For Llama Index, you would import a GPT tree. Basically, you just load your document into the method and put into a query engine. A query engine basically takes your input and then puts into a vector store. For LaneChain, you would need to import a vector embedding and a similarity search. That's basically your retriever. So first you need to create your embeddings. What this does, it basically changes your raw data into vector embeddings. So here I use OpenAI embeddings, and I put that into embeddings model. And then here FAISS stands for Facebook AI Similarity Search. What that is, it basically takes the relevant vectors and does that for you. So here I just store into a variable called index. So here's a diagram of how vector embeddings work. For example, I have king, man, and woman. The vector, the little diamond thing is the vector, the embeddings model, and it changes that into vectors. So as you can see on the graph, the similar words like apple, banana, orange are more close together on the graph. And then this makes it easier for your retriever to get the relevant data. All right, so here's a diagram of how a vector database works. This is basically Facebook AI Similarity Search. You see the red diamonds, those are your data and they're stored in clusters, which is like shown with the little circles. And then the system indices makes indices for these clusters. So it's easier for the similarity search to get relevant vectors. So basically, when you input a query vector, that's basically your question. It turns that into a vector as well. And then Facebook AI similarity search finds the closest vectors to that index, which means it gets the relevant data. All right, so let's go over how each of these two frameworks actually get your data. For Llama Index, it uses a tree-like structure for efficient retrieval of embeddings, and it can be more efficient than a vector database. For LangChain, you must manually embed and then index from there. The purpose of this is that it supports many vector databases, such as Facebook AI similarity search, Pinecone, Chroma, and more. So here's some code of chains. For Llama Index, you would just put into a query engine and ask your question from there. It basically does it for you. For LangChain, you will need to import a retrieval Q&A and a OpenAI model. So the OpenAI model is stored in a variable called LLM, and then you ask your question from there. Here is another diagram of how it works. Basically, you just take your source, you load it, and then you transform it, which means you split it up, and then you embed it into vectors, and you store that, and then your retriever retrieves those relevant vectors. So here are the types of chains in LangChain. There's a module called langchain.chains with pre-built chains you can use. You can also build your own chains, but you can also use the module that they give you. Here are two basic ones. Simple sequential chain. It's a basic chain that runs multiple LLM chains. The output of one of the chains becomes the input of the next. For sequential chain, it's more flexible and allows for multiple inputs and outputs. All right, so you can also chain multiple LLMs. LangChain allows you to chain multiple LLMs and have multiple retrieval support. And it's great for complex workflows. Here, OpenAI is communicating with BERT. Here's some sample code of chaining multiple LLMs. I import the simple sequential chain, and then from LangChain, I import OpenAI, and then from Hugging Face Hub, I will import the BERT model. So basically, I have a GPT chain, and I chain that with GPT, and then I give it a prompt. For BERT, I do basically the same thing. I import BERT large uncased, which is a LLM model, and then I also give that a prompt, and then I chain them together using simple sequential chain, and then I have my result with my question. All right, so now let's go over our demo.
Share my screen. Let's do it. Okay, that was not recorded, but anyway, so we started recording now. This is the Wally script, and you can take a look if you want. It's quite a long script. It's like 95 pages. I didn't really read it through. I think it will be too much trouble for everyone to read it through. I just turn on the audio. Oh, it was muted for the first 5 minutes. Anyway, so that's just for you guys to know what is in this PDF file. But once you have run this code, okay, it's connecting. Once you have run this code cell, you'll be able to find the downloaded script. Okay, it should be here inside the files. So if you look at here, I have this Wally underscore script PDF in my code, in my directory. So that's good. We have secured the movie script, and that's something we can work on to rebuild Wally's memory to help him out. Yeah, we will be rebuilding Wally's memory using RAG, and we'll be using this framework called LangChain. So I know Jeff talked about 2 different frameworks, LangChain and Llama Index. I personally have more experience with LangChain, so that's what we are basing this demo on. So basically, we will be doing a lot of stuff with LangChain. We will be loading the original script that we just downloaded. We'll be breaking it into smaller chunks, and we will also be searching relevant information when a question is asked. And finally, we'll be using ALM to construct the answer alongside the information that we searched up in the previous step. Let's get started. And I think this part is meant to be like a review or something for the concept of RAG, but things just covered it. I'm not going to go too deep into it. You guys can take a look if you have the time or if you're more interested. But basically, RAG is just a way to equip ALM with some external knowledge dynamically. So it's more powerful than the language models that everyone uses, like GPT. GPT do not know your personal data. For example, it does not have access to some of your company restricted access file or something like that. But if you want to have it do something that's related to those files, you have to feed it in order to have it work properly. So yeah, here is a more technical question mark definition. So R stands for retrieve, A stands for augment, G stands for generate. I'm pretty sure Jeff talked about it earlier. But yeah, so the reason why we thought this is useful is you don't have to fine tune a model. Again, you can give it, you can have different data that's being handed to this large language model, and you don't have to have any changes on a model itself. It's just the difference of the input that you're giving it. And of course, you don't have to update data. You can update data without retraining, as I said, and it keeps answers grounded in known sources. So that was a long review, kind of. And some more review is about, what is LangChain? Pretty sure Jeff covered it in the earlier part of this workshop, but LangChain is what we use to connect all different parts of a LLM app together. So we have the LLM, we have the retriever, we have the embedding model, we have the loaders. All these parts, they're great, they're awesome, they do their stuff, but the thing is, they won't do anything that means anything to us unless we connect these things together. So LangChain is like the chain that chains these things together. That's really important. And we don't really have to write a lot of complicated code. As you guys will be able to see, we will be only writing very few lines of code to achieve a very obvious effect. So yeah, let's finally actually get started. So the first step that we need to do is to set up the environment. We need to download some useful tools, some useful libraries, packages that we need to use for this project. And I'm pretty sure you guys have the Gemini API key, or you guys learn how to make one in the first workshop that's covered by Lorelei and Kian. If you don't, I encourage you guys to create one right now because we'll be using it throughout this project. And as I know, it's free, so why not? You just need a Google account. I'm pretty sure you guys all have a Google account. So make sure you have a working Gemini API key, and we will be starting to install the packages. So the first thing that we need to install is, of course, the LangChain package. We're using LangChain. You, of course, need to use the LangChain package. And aside from the main LangChain package, we also need to have some, like add-ons. That will include LangChain Core, LangChain Text Builders, and LangChain Google Gen AI, which is pretty self-explanatory, the library that helps us to interact between LangChain and the Google Gemini API. So there are other stuff that we need to install, including PyPDF, which is a library that enables us to work with PDFs. in a LangChain app, and also sentence transformers. We'll be talking about what they are in a bit. So yeah, just go ahead and click on installing, and it will take a while. I think it will take quite a while. So while it is working, I'll just kind of go over the next couple of code cells. Yeah, it's gonna take quite a while, especially for the second and third command, but just go ahead and run it. And for the next steps, I'll go ahead. Which file are you currently on? Because we have two different versions. Previously, we were using OpenAI, but we figured out, if you have to pay for OpenAI, so we kind of changed it to using Gemini. So you might be on like a previous version, but I think if you just visit the link. Oh, are you in like the GitHub repo? Yeah, I have not uploaded the new version to the GitHub repo, so you might have to, go from the slides, click on that link, and copy that file. Yeah, just make sure that you're passing your Gemini API key, not your OpenAI API key, because you're not supposed to. And if you are, that means you're on the wrong version of the demo code that we're working on. So yeah, as you can see, it's still installing. So I'm just gonna go over some of the later cell blocks. So after installation, we need to, I did not change the comments. But anyways, you need to load the API key. In this case, it's our Google API key. And here I'm using a function called getPass to help us securely upload our API key. And once the previous cell finished running, I'll put in my API key, and you guys can put in yours as well. And let me know if it works or if it does not work at that point. If it not, something probably went wrong in your setup. And after that, after we have our API key, we need to set up our embeddings model that we will need later. And here we are also using LangChain Google Gen AI, so just make sure that you are using it instead of some OpenAI version. And after that, we will need also to set up a in-memory vector store. So that's basically going to be where we're going to store all of the data that we're searching later on. So yeah, I'll be explaining more of what in-memory vector store means later. Or actually, I can explain it now. So we're here using a in-memory vector store. That means we're not going to store the data anywhere, on our disk, on a USB drive, or anywhere. It's just going to be in our RAM. It's just going to be in our temporary memory. So if you rerun this code, if you run it on somewhere else, data will all just be lost. So it's not really good if you want to have some sort of persistent database, persistent data storage, but it's perfect for our purpose because we don't have that much data. And this is just a very short demo, so we can afford it to just have all of the data stored in our temporary memory. And we don't really care about it after we're done with this demo, so we can just discard it. So it's perfectly fine to use an in-memory vector store. But if you're thinking about, building anything serious or anything large, anything that you want to be persistent, maybe check out other vector stores that can have those options. So that's finally done, all the installations, and I'm now gonna load my API key. So how this getPass function works is that once you run this function, it will prompt you to enter your API key for the corresponding producer. And I have copied my API key onto my clipboard so that you guys won't be able to see it. Anyways, I hope you guys don't see my API key. But anyways, if you copy paste into the chat box and you hit enter, it will load your API key for this session. And if you rerun this notebook, if you delete this current runtime, if you reconnect, you will have to do this again. All right, so I'm ready to run the remaining cells. Set up embeddings model. Okay, running, done. Set up in-memory vector store, done. Set up chat model. Okay, after you have set up all of these things, you can go ahead and run the last cell of this section, which basically checks if you have all of these things ready. And if you see this check mark, that means you're good to go. If you see something else, that means you're, go back and check where you have done run. Okay. Is everyone okay? Can I get a show of hands of how many people are actually like trying to code along? Or okay, are you guys doing all right? Still waiting for installation or done? We're done? Okay, we can move on. So, okay, just a quick note before we move on. There is a possibility that one of you guys are not a fan of Gemini. I know people like that exist. I know people are just, crazy fan of OpenAI. I know people like that. But what if you want to use something else? What if you don't want to use Gemini? What if you don't want to use any of the Google products? That's perfectly fine. Because LangChain is really flexible in terms of what set of tools you are trying to connect. So you can easily swap out these different components that I have set up earlier to fit your needs or preferences. So something that you can try out is you can swap out for different LLMs. You can swap out for different vector stores, as I said. You can swap out, or like you can choose to run your models locally or on the cloud. So that's all an option. And even better news is that you don't have to do much work to make all of these changes possible. So basically, the only changes that you would need to make will be inside these code cells. And it's not much code if you look at it. And everything that comes after these, you wouldn't really have to change it. They will just absolutely work normally, work perfectly the same. So if you are looking at my GitHub repository notebook, you will be able to see that everything that comes after is exactly the same. I have only changed the libraries that I'm using and the set of code that I'm using here. That's it. Everything else is the same. That's good news. That's just something that I really like about LangChain. It's very plug and chug, and you don't really have to think too much about it. All right, we're finally ready to get started. The first thing is we want to load the PDF file that we have downloaded into our entire software system or LLM app. You have anything to ask? Question mark? Anyways. All right, so this will become the memory source for Wally, and he can reconstruct his thoughts based on this memory of information. So to do that, we will be using this thing called PyPDF Loader that's provided by LangChain. Basically, what this library or what this tool does is that it extracts text from each page of the script, and it's returned as a list of documents that you could, inspect and see and check by yourself. And over here is the first code cell that we need to actually fill out. It's actually just a one-line code, so pretty straightforward. But basically what it does is that it will load the PDF script into Wally's recovery core. So what we're going to do is, so we're going to set up a loader that's called PyPDF Loader. PyPDF Loader. And the name of the script, as we have downloaded, is Wally _script. .pdf. So we have set up the loader, and we want to have a variable that stores the pages that we read in. So we will be calling those pages, and it will be an empty array. And to load that, we'll be using a for loop. We'll be reading the pages one by one and load these pages into our pages variable. So to do that, we'll just be calling pages for pages and loader.load. And we'll be saving these for page in page. Pages append page. All right, looks pretty straightforward. Let's try running it. And it doesn't really seem to do anything. So we want to check, we want to inspect to see if the script is actually loaded. So to do that, we run the next code cell. And we see that, hey, it says that we load a total of 95 pages. And there are some metadata about the first page. And it also printed out the content on the first page. So you can see that, there's some fading, stars, a beat show tune, stuff like that. So it seems that it works. And are there any questions so far? Is anyone having trouble with loading a script? Okay. I'll leave this code up here for like 10 more seconds. Okay, so let me just explain the output for a little bit. So as you can see here, we got back the page content, which is apparently something we want, of course. But we also got back some other information that's called the page one metadata. So you can see that here, what we got back is, okay, this script was produced by Adobe Acrobat, and it was written by, this author, and it has this creation date and moderation date. These are very helpful information, just not in our project. So This is useful for debugging, understanding file structure, or even filtering out specific pages. But for our project, for our purpose, we're not using any of these metadata, but just keep in mind that those exist and those might be useful if you're working on something else in order to achieve some different purposes. So yeah, we don't have to worry too much about it, just to make sure that you guys know that it's different. That was our first step. So right now we have loaded our script into our program. So does anyone have any questions, or are we doing good? Should be a pretty chill setup. Okay, so that was the first step. And for the second step, we want to try, feed Wally all of these information out of the script, all of these pages that we have got. So let's just try feeding him the entire script. That's pretty quick, pretty apparent, pretty convenient, straightforward. So we gently place the documents into his input slot, and it just did not work. He was not able to handle that many information in one run. And as unfortunate as it may sound, it is some actual problem that we face every day when we're dealing with our LLM. I think a couple of days earlier, I was trying to work on an assignment and just copy pasted the entire spec into my ChatGPT account, and it refused to process it for me. It was like, too much text, cut it down. I was like, okay, fair enough. So I, cut it into 2 halves and feed it the first half first and the second half later. I'm pretty sure some of you guys have had that similar experience previously. But the reason behind this is that those language models, they can only see a fixed number of tokens at a time. So if you copy paste the entire spec of your CS32 project in, it won't be able to handle that many tokens at a time. So that fixed number of tokens is called the context window. So as you can see here, GPT-4 has a context limit. It's large, but you can still surpass it with enough amount of text like the CS32 project spec. And if you try to import more than that, the model will ignore or truncate the access or refuse to process these data for you. So in order to have Wally take in all these information, we need to help him process this massive amount of text. So what we're going to do is these 3 steps that I have listed here. First thing that we need to do is, of course, what I did. We need to split the scripts into smaller chunks that he can handle one at a time. But there's something else that we need to do. We also need to overlap these chunks to maintain the overall context and also track the original position of all these different chunks in the document. Why we need to do that? We need to, we just split it up and feed it all into Wally's memory. What's wrong about that? Yeah, it's pretty wrong actually. So if I can just give an example, let's just use this line of text as an example. Let's just say that this line of text language model can only see a fixed number of tokens at a time, known as the context window, is our document. I mean, it's a pretty small document. I'm pretty sure any LM will be able to handle it, in a whole. But let's just assume that the context window is only 5 words at a time. So we would have to split the script or split the document into 5-word chunks. So our first chunk will be, language models can only see, and the second chunk will be a fixed number of tokens, and the third chunk will be at a time known as, and the last chunk will be the context window. If we do not have overall context, if we do not have original position, maybe the program will just read it as the context window, a fixed number of tokens language model can only see at a time known as. That just do not make a lot of sense. You guys can all probably see. So that's why we need the context and position. And rest assured, it's not super complicated to code out. It's not complicated at all. LangChain handles all of these for us through this tool called recursive character text splitter. So it intelligently breaks documents based on structure. So it will try to cut at paragraphs if possible. If that's not possible, it will try to cut at complete sentences. And if that's not possible, it will try to cut at words, of course. But it will try to maintain the overall context and the overall meaning of the document whenever possible. So that's more talking, and we have one more code cells to fill in. So over here, we have imported the recursive character text splitter, and we actually just need to set up the text splitter. So to do that, we'll just set up a variable called text splitter. And to do that, use, Okay, I created a bunch of empty box. Anyways, so use this recursive character text bidder and set it up with some parameters. So there are 3 parameters that we really care about. The first one is, of course, chunk size, how large we want each chunk to be approximately. So we want the first chunk to be, or like we want each chunk to be 100 characters. And the second parameter that we care about is, as I said, the overall context, and we will be achieving, or we will be maintaining the context through overlaps in these different chunks. And we also have to specify, how many characters we want in each overlap. So to say that, it will be saying chunk overlap, and I'll make it 200 in this case. Pretty solid. You can make it different with your own parameters value, but I mean, it probably all work the same or similarly. And the last thing that we care about is their original position in the document. So the last parameter that we need in this case is add start index. All right, so that's all the parameters that we need to set up the recursive character text bidder. And one last thing that we need to do is to actually run this text bidder. To do that, we'll be calling this function and using this text bidder to split the document. Split documents. And here we pass in the variable pages. And if you remember, that's where we store all the PDF pages that we loaded in previously in step 0 or in step 1. Yeah. All right, so we're ready, and let's try running this. And it said, okay, split script into 159 subdocuments. So that looks pretty solid. I mean, I didn't really look into each of the chunk, but it looks pretty niche to me. We have 95 pages, and each page is split into about 2 documents. So that sounds pretty all right. Just some more details about how this code works. You can read it if you want to, but this is basically just what I said when I was explaining the code. The text bidder is trying to split text at natural boundaries. So as to mimic how human will try to split up and understand a document. And if no good boundaries are found, it will just fall back to the smallest unit. All right. Okay, this should look something like this. So if you see the progress bar, you can see that, okay, awesome. We're chunking, we're overlapping, we're doing some additional processing. And finally, we have all of our 159 memory fragments generated. So that's nice. That's good. We're done with step 2. Is everyone still coding along, still following along? Does anyone need more time or any questions, or should I slow down a bit? Or okay, fair enough. I would assume that you guys are all following along because it's not a lot of code. It's mostly just me yapping, as I said. Anyways, that was the first 2. Oh, go ahead. Yeah, like normally you just experiment, and for our case, because 95 pages is a lot for us to read, but it's not really a lot for the program, so I kind of just set up that like arbitrary value. Of course it wouldn't really be reasonable for you to set up like a 10,000 word chunk, so I kind of just randomized that value. But yeah, if you're doing anything serious, you would have to tune that. You will have to test out a bunch of different values to see which one works the best. And you will be, using that value from then on. So yeah, in one word, we don't really care about it right now. Any value would work, any reasonable value would work in our case, but you would need to think about it if you're working on your own project. Any other question? Want a squishy by any chance? Okay. Oh, these are good. Why is this? Unfortunately, no one wants them. All right, we are ready to move on to the next step. So now we have the documents. We have split the documents into chunks, and we're finally ready to upload these chunks into Wally's memory module. But that will mean the vector store. So unfortunately, Wally does not function as we do. So we understand text and we memorize text and we process text naturally because we're human, but Wally processes things differently. So it handles something called the embedding, and embedding is a numerical vector that captures the semantic meaning of the text. And this is an example over here. Make sure you can see the entire graph. Oh. All right. So yeah, this is a embedding example of this group of words. You can see that there are grandfather, man, adult, woman, child, infant, stuff like that. And we're representing all these words on a two-dimensional grid. So you can see that on the x-axis, we have gender, and on the y-axis, we have age. So naturally, grandfather will have a higher value of age than boy, because grandfather has a higher age, if you are wondering. But adults also have a lower value than women on the axis gender. So if you look at it like more carefully, I'm pretty sure you guys will all be able to figure out what this embedding thing means. So that is a very simple example. In real world, in real cases, word or sentences will have definitely more than 2 dimensions. So it will have probably like thousands or at least hundreds of dimensions, and we won't be able to visualize it on a graph, or sometimes we can't even imagine it. It's just like the dimension is just a number. It's not like a graph or anything. So yeah, like in real world, it's a lot more complicated than this, but this is a good starting example. So these embeddings can be created using a transformer model. So if you still remember at the beginning of this demo, we installed and imported something called sentence transformer. So that is the thing that is used to transform these texts into embeddings. So we will be using that actually here later on, or not later on. Anyways, so that's the embedding process. And after we have all of these embeddings, we're good, we're chill, we're done with the processing. We need somewhere to put these values because we will need to search from it. We will need to retrieve some of it later. So the place that we store and retrieve these embeddings is called a vector store. So vector store is a searchable database that's optimized for similarity-based retrieval. So it's somewhat similar to a vector database, if you have heard of that term. But I think, in my opinion, vector store is just more focused on the storing and retrieving and searching. So it does not have a lot of the functionalities that a vector database would provide, but it's necessary, it's sufficient for our purpose. So we won't really be needing a vector database here. Vector store is good enough. So yeah, these are very complicated ideas, but again, very fortunately, we hardly have to code anything out because LangChain abstracts all of these complicated ideas very nicely, and it handles all of the interfacing and heavy lifting. So all we need to do is to write a single line of code to make all of these possible, make all of these work. And the code that I'm going to write is called document IDs. Oh. And we will be grabbing this information from the vector store that we set up earlier. And the function that we're going to call is called add documents. And passing in documents that we split up earlier. It's called all splits. So, all right. That's it. That's all the code that we need to write for this cell. And let's just try running it. Oh. Okay. Oh, my API key expired. Anyways, okay, we have some trouble over here. Let me just give me 1 second to update my API key. I'm gonna stop sharing just in case you guys see. All right, meanwhile, you guys can look back on the notebook that I had and ask any questions if you have any. Hey, I promised it was working yesterday. Oh. Did it work for you? Okay, sounds good. Yeah, turns out as long as you don't have the API key that you generated yesterday, you'll be fine. But if you don't, you're fucked. Oh, I shouldn't have said that. It was recording. I'm generating one. Yeah, I've generated one. Yeah, I don't know why it expired so quickly though. That just does not make sense. Wait, I can't have uploaded it somewhere, right? There's no way for me to upload it somewhere. the thing is, if you do upload it somewhere, maybe it will get detected and people will say,
It'll give you an email.
yeah, I didn't get that email. Oh, I shouldn't have run this again. Oh, that's fine. Anyways, I mean, we're probably gonna wait for a bit because I'm rerunning the entire notebook. That means I'm rerunning the installation of all the libraries, and so it's gonna take a while. Oh, it's not gonna take a while. Oh, interesting.
Beauty of computer science.
Oh my god, that's just weird. Okay. Actually, I'm gonna do something that I'm not supposed to do. Oh. Definitely not do it. Huh? Yeah, I think this is the last part.
Okay, for those of you that are following along, if you put your own API key into it, is it working? Okay, so that's what matters.
Oh, wait, no, I know. This is because it's not executing the if statement. Not debugging right here. Oh.
Okay, this is the hardest CS.
Okay, okay, we're ready to go. Anyways, okay, I
Cheers,
better remove this. I better remove this. Oh my god, I am dead. Anyways, just gonna remove this. Okay, I am ready to be back online. Okay. All right. Yeah, turns out my API key was expired for some reason. It seems that Gemini has a very short time to live value for your API keys. So if your API key, or if you see an error, probably just generate a new API key. So yeah, I have a working API key right now, and I just ran this code cell, and it finishes. I mean, you don't really see anything. You don't really get like a congratulations return value, but you know it worked because if you just print out a few document IDs, you will see that this, random list of document IDs looks totally unreasonable, but it's proof that your thing worked, and these unique IDs are actually very useful to our program. We might not be able to understand it, but our program will be able to use these IDs to reference, update, or delete specific documents. But for our purpose, again, we're only using these IDs for retrieval. We're not altering our documents in any way. So that was it. That's just very simple for embedding and vector store storing. Now that Wally is fully equipped, it's ready. It's, like we can start asking him questions. There's just one more thing that we need to do before that final question asking part. We need to construct the stop pipeline, and that's basically the RAG chain, the RAG chain that Jeff talked about earlier. The chain works as first you ask a question and the program accepts a question, and then it searches for the vector store for the content that it is most related, that's most similar to the question that you asked, and it searched for the relevant memory chunks, the relevant information, the relevant document, and then it takes the relevant documents and it feeds those documents to the language model, and the language model will work based on both the retrieved documents and also your question to construct a answer. We're almost there. Rest assured, this is a long demo, but we are almost there. Just need to connect the dots together. Final step, reconstructing slots, and yeah, if you scroll down, we only need 2 more code cells to fill in. So that's good news. And just one more side concept, I guess, that I want to introduce is prompting. So in an RG pipeline and RAG pipeline, it's just not enough to retrieve the relevant documents because the program won't really know what to do with these documents. You need to have you have to give it like a clear objective of what you want it to do. So in this case, the way that we tell the language model how to use these documents is prompting. So a prompt is the actual input string that gets sent to the language model. So you would think that, when you're talking to ChatGPT, your prompt is basically just your question that you input in text box. Well, that is not the case. It's actually more than that. Of course, you have the question, the user's question, but you also have, in our case, the retrieved context, the retrieved documents from the vector store. And sometimes there are other stuff like formatting information. For example, you want it to be formatted in Markdown or formatted in HTML or HTML or something like that. There might be other instructions like answer concisely or use Markdown, as I said, something like that. So yeah, these are some of the main information that a prompt will include. So we will be using this sort of like prompt to pass the information, but we don't have to hard code all of these templates, these prompts by ourselves. So instead, we'll be using this thing called LangChain Hub provided by LangChain. Basically, it's just a database, it's just a registry of all the prompts that's already being built by others, and we can just use them directly. We don't really need to build our own stuff. So it's really convenient and ready to use. So here, we're using a popular one for retrieval augmented generation. You can, visit LangChain Hub and see if there are any other prompts that or prompt template that you're interested in. But for here, we're just gonna use like a very general purpose one. So yeah, to do that, we will be importing this hub, and we will be constructing this prompt by pulling from the hub. And there is a specific name for the prompt that we're pulling from LangChain Hub. It's a generic RAG style prompt, so it's just called RLM and RAG prompt. So, all right. So let's run that, and you will see this warning by Landsmith. You don't have to worry about it. I don't know why it's here. I did some research. Apparently, our code is doing some gibberish with this thing called Landsmith, but we're not actually using Landsmith anyways. So if I were to explain it, I would say it's something like you got into your car and you're ready to drive, and suddenly there's a warning telling you that, oh God, there's no GPS signal, but you don't need GPS signal. You know where you're driving, you know how you're driving there. So it's something like that. It's a warning, but we're not using it, so we don't really care about it. And you'll be able to see that our program, our demo still works with this warning. And this is a warning that a lot of people have seen online, and they don't really say anything about it. They just keep going. So yeah, this is how the prompt actually looks like, by the way. It says, some information. You're an assistant for a question answering task. If you don't know the answer, just say that you don't. Use 3 sentences maximum. Keep answer concise. The ordinary stuff. And the question, the input question is filled in here. And the context, which is the retrieved documentation, the retrieved vectors are filled in here. And finally, the LLM is supposed to fill in the answer. So let's just try asking a question and see if Wally is able to spit out the correct answer right now. So construct a question. Here I'm going to ask a very basic question just to see if it works. I'm gonna ask, who is Eve? And step 1, we want to retrieve the relevant documents using similarity search, and we'll be using our vector store. So retrieve docs is vector store. And since we're using similarity search, just be saying similarity search and search for the question. All right. So that's step 1. And step 2, we're going to combine these pages, these documents that we retrieved into a single document, into a single context. What we retrieve might be an array of documents, but we don't want to feed our LM an array. We want to feed it a single document. So we're just going to combine off these documents that we retrieve. To do that, we'll just say, docs content, combine it with probably 2 returns and join all of these docs. So yeah, here we don't really care about the metadata. As I said earlier, we only care about the page content. So we'll be retrieving the page content from each doc for each doc in the retrieved docs. All right, so that was step 2. And step 3, we are ready to provide the question along with the context to the RAG. And to do that, we'll construct this thing called final prompt. And constructed with prompt and calling invoke on this prompt. And we'll pass in two things. The first thing is question, of course. And the second thing will be the context, as I said earlier. Docs, content. All right, so that was the construction. And finally, we're ready to get back the answer. Last thing we need to do is invoke the LLM and have him spit out the answer. All right, that was our entire chain. As you can see, there's a lot of steps, or there are a decent amount of steps, and each step we're just connecting these dots together. We're not coding the similarity search. We're not coding, okay, I guess we're coding some sort of combining here, but we're not coding the invoking function of the prompt, and we're also not calling the invoking function of the LM. We're doing a bare minimum. Let's just try run this. And it finished running, and let's see what answer we get. All right. Based on the provided text, Eve is a female robot with blue eyes. To be completely honest, I never watched WALL-E, so maybe one of you guys can tell me if the answer is right. So basically it says that, okay, she can emit a blue ray to scan objects and areas. Oh, that's pretty cool. She is also associated with a plant and has a directive. Very interesting. I am assuming that is wrong because no one told me. I'm assuming that is correct because no one told me that was wrong. But it seems that our RAG is working, and you guys can just, ask WALL-E a different question or do something about it. But yeah, our mission right here is completed, and WALL-E remembers, and you have just built a working RAG system. So there are a lot of stuff that we did. A quick recap. We used an engine to load a document. That document is a real world document. I did not make it up. I just Googled it and found this document. It could technically be replaced with any document that it can access. We also split this document, this quite long document, into smaller, reasonably sized chunks. And after that, we turn all of these documents into vectors, some form that our program can actually understand. And we stored these embeddings into a searchable vector store. And finally, in the end, we connected all of these parts together and built a fully functioning end-to-end pipeline. All right, so that's a very simple demo. That's a very simple example. I'm pretty sure you guys all know that this won't really get you into a YC or anything like that. But this same pipeline can be adapted for something that's more complicated and that's of more real-world usage. So that will include something like a document QA system. That document can be any document, that might be your company's technical product documentation, something like that. It can also be used to build some chatbots with memory. I'm pretty sure you guys have all, seen or heard something like that. It's pretty popular nowadays. And it can also, provide customer support. Sometimes when you're trying to get your customer support, you'll be able to see that, okay, this is apparently a robot. I'm not talking to a real human. Get me a human representative. But maybe someday these RAG assistants still be powerful enough that you won't be able to, or like you won't need to call a human representative. They will just do the work as good as well. All right, so that's the end of our demo. Before I end, does anyone have any questions? And can I get a show of hands if anyone is following? Did you guys get it to work or not? Work? Okay, work. I'm assuming some of you guys are just following or just looking at my uploaded GitHub repository or like GitHub notebook, question mark. Are you doing that? Are you coding? Okay, sounds good. Okay, that's good news. Yeah, I think that's it for our first workshop. Do you have like a break or something? Sounds good.
Own retrieval augmented generated function in a Python notebook. Okay, so before we go into the second demo, if you guys don't have any questions, we're gonna have you guys line up for snacks and boba. But before you do that, make sure that if you haven't signed in already, please sign in with your UID because we do need to do that before you guys can get snacks. Yeah, we don't want the boba to melt. We want to give you guys a little break. Okay, all right, everybody, we're gonna get started again. Okay. I hope everybody enjoyed the food and the boba and you guys are re-energized for part 2. This is a completely separate use case of AI wrappers. presented by Sebastian and Arnav. So I'll let them take it away.
Okay, so we're gonna demo something that you may have heard of before or something you may not have heard of before. It's called a multi-agent network. So maybe you've heard of this before, and agentic AI seems to be the new thing. Like everyone keeps talking about it, and all these new startups keep spawning using agentic AI. So we're gonna explain exactly what that means and how you can make an agentic system of yourself. Okay, so I'm gonna start off with what is an AI agent. So a language model. So an AI agent is a language model that can make decisions, take actions. It can receive input through a task, and it may use tools to get answers. The way this compares to like a regular model like ChatGPT or like Gemini is that ChatGPT, you just give it a prompt and it does whatever with it, and using its trained data, it'll output an answer. But you can actually go beyond just that text generation output of ChatGPT, and you can use specific tools to like search the web, use calculators, read files, call APIs, and even run code. So you can kind of segment that process of ChatGPT, and you can use it for like complex and multi-step tasks. So when a task needs planning or you need to have like specific modular instructions, that's what an AI agent is perfect for your project. So what exactly is a multi-agent network? So a problem is that one AI agent with too many tools or tasks can struggle. So if you notice, like, I don't know, if you've ever tried to summarize like a GE essay or something, and you put in like a giant block of text, ChatGPT may kind of skip over a lot of elements, or it won't really respond to the depth of detail that you want. So the solution here is that you can create a team of specialized AI agents that can handle each process of that task that you give it. That way, each task will be able. That way each task will be able to be done more, I guess, more to its full potential. And how it works is that each agent is an expert in one area specific to a domain that you define. So for example, if I'm doing research, I can have one agent do the research and one agent kind of evaluate my research. That way I'm not overloading one model with all my information. And the benefit of this is that you get better performance, and then each agent focuses on what it does best, and you will ultimately usually come out with a better product. And we call this multi-agent network a multi-agent network. So what are we building today? So our specific demo will be focusing on a multi-agent app for evaluating startup ideas. So for example, if I were to give my app a startup idea, it could do the research and all the evaluation and determine if my startup is actually viable based on like real-time market data. And we can make this through a series of agents. And pretty much how it works is that user would give a startup idea, and then our app, and then this idea will go through our multi-agent network pipeline, and then we can figure out how viable this idea is. So I'm going to give you guys a brief showcase. Okay. So does anyone have a startup idea that they think would be good? If not, I can just come up with one.
Or bad.
Yeah, or bad. Sure. Okay. So no one has seems to be having a. Oops. Okay.
What?
I'm gonna just get my API key. So we have the API keys on the sidebar just for. You can copy that down. I'll just change it later. But we'll have our API keys on the sidebar just for ease of use. So I'm just putting them in right there. So I guess a startup idea that is bad would be like a penguin, like a subscription service for penguin food for Hawaiian residents, because there's no wild penguins in Hawaii. So I say like a subscription service for penguin food for Hawaiian residents. Okay, I'm gonna click submit, and we'll come back to this later. I'll show you at the end maybe, because it does take a little bit to run because it's going through an entire pipeline. Okay. All right. So if you guys want to follow along to this tutorial, you can either go to the GitHub. It's going to be in part 2 of the workshop series, or you can actually clone it on your own machine by typing that clone command up there as you did for the first workshop. Okay, Sebastian's going to explain a little bit.
Okay, so we're gonna be using 5 main different technologies today. That's gonna be our technology stack. So we're gonna be using Gemini, Pabbly, LangChain, LangGraph, and Streamlit. And if you're familiar with any of these, no problem. We're gonna be going through every single one in depth. So first of all, we have LangChain and LangGraph. LangChain is a framework for building LLM-powered apps. So it's a framework that provides us with components that makes it easier to build. It lets us build agents. We can like give it specific tools, and it also has built-in memory management, which makes things a lot easier. It also simplifies the syntax for API calls a lot. So instead of using the OpenAI API directly, for example, or Gemini API directly, we're going to be using, it's going to go through LangChain instead, which simplifies the code. And yeah, it integrates with a lot of different LLM and tool providers. Just to name a few, we have OpenAI, Gemini, Claude, Pabbly, but there are basically endless possibilities here. Then we have LangGraph, which is a LangChain library for multi-agent workflows specifically. It lets us build a graph-based execution model. We're going to go through what a graph is later, but it's just a way to think about how the different agents communicate with each other. It lets us do this through built-in functions called state graph. And it lets us build like a very structured coordination and looping between the different agents. It also has built-in state management, which makes it much easier to keep a message history, for example. Let's say you're building a chat bot. It makes it much easier to like have your app take all your like past messages into account. Then we have Gemini and Pabbly. Gemini is the LLM provider we're going to be using today. We could hypothetically use any LLM provider that's compatible with LangChain. For example, OpenAI, but we chose to use Gemini today mainly because it's free. OpenAI is paid. And also Gemini is among the leading models. So that's the reason we went with Gemini this time. We're also going to be using Pabbly, which is a web search tool for AI agents. So the way we will use the Pabbly tool is to have it conduct web research for us in real time. And then this information will be fed back to the other agent. It's important to note that Pabbly is just a tool, it's not an LLM. So for the agent using Pabbly, we'll still have an LLM in charge that will then use Pabbly as a tool. Also, we're going to be using Pabbly in this workshop specifically, but there are so many different tools. Just to name a few, you could give like Wikipedia API to one of your agents, so you can use Wikipedia as a tool. PubMed tool, for example, for medical research, or read file tool if you want to input files. So the opportunities here are basically endless. Also, just quickly, I'll show you how to get a Pabbly API key. You don't have to do this right now, but just so you have a vague idea of how it's done. So you basically go to their website, pabbly.com, then press login. You'll get the opportunity to register as a new user. And when you've done that, you come to this dashboard, and from here on, you can just press the plus button here to create a new API key. You can give it your own name and just use it from there. So it's very, very simple. The final technology we're going to be using is Streamlit. Streamlit is a Python framework for building interactive web apps. The reason we're using Streamlit is because it's extremely easy to use, super simple. easy syntax, and you can keep everything in the same file. It also runs locally, and if you want to deploy it at some point, Streamlit has its own service called Streamlit Cloud, which can like help you deploy it very easily. And when you put in all your syntax, it's also very easy to run. You literally just write this, like run this in your terminal, Streamlit run, and then your script, and it'll give you a link to like see it in the browser. We'll go through exactly how to use Streamlit later in the workshop.
Okay, so now to get into the actual multi-agent architecture overview. So as I mentioned before, we want our agents to do specified like modular tasks, and we want that to be kind of fueled by a prompt. So say I'm a user and I want to evaluate the potential of a startup idea of a company that compacts and recycles used robots. So first I'll have two agents. I'll have a researcher agent, which kind of I briefly explained this before, but it kind of conducts research on the like startup viability of my idea. So it'll go to the internet, go to various sources, and we'll be doing that through Tably, and it'll conduct the internet research. And once it has internet research, it won't do any actual evaluation of how good the research is. We'll send it to another agent that evaluates how good the research is and how this research can be applied to my startup idea from the prompt. And this is not a one-time operation. We'll go back and forth between the researcher and the advisor until one of the LLMs determines that we've reasoned enough and we have a final answer. And then once we have a final answer, we'll go back to the user and then we'll kind of give that final answer back to the to answer the prompt. Okay, just a little bit more logistical stuff. We're gonna need to install some Python libraries in our project. You may have heard of a virtual environment before, or you may not have. But the reason we want to use our virtual environment in Python projects is to kind of containerize what we're downloading. If we were to download everything on our main machine, it gets kind of messy really quickly. If we're working with multiple projects, we're going to have a lot of libraries just installed anywhere with stuff we don't use often. So for each project, we want to create something called a virtual environment that kind of holds all our libraries for that project. You don't have to do this right now as well, because you can just look back on the slides later and follow along. But I've included some quick commands that you can just do to quickly create and activate your virtual environment inside your project directory. And then also, this is just a continuation of that. These are the packages that we're going to be using. If you look in the GitHub, we'll also have a file called requirements.txt. So if you don't want to type all that out, you can just copy the requirements.txt over to your project directory and just type that in. But this is also how you install packages once you've created and activated your virtual environment. You don't have to do this now because it might take a little bit, because some of these packages are pretty big. But this is just for your reference for when you're actually.
So we'll start with a brief Streamlit setup, just so you know how it works. We have to start by importing Streamlit at the top of our file. So that's just a simple import statement. Import Streamlit as st is the standard here. And from there on, you can create UI elements. Just name a few. We have title, sidebar, input, text. There are like everything you need. Streamlit has. They offer everything you need, basically. So just so you can see here how it would look like. This is our website for the startup evaluator. To create a title, you would basically type st title, and in the parentheses, you would then type the title name, which in this case would be startup evaluator. We have a few other examples here. This to just have some plain text, you can use st.write. For a warning down here, it says please enter your API keys in the sidebar to continue. This is a Streamlit warning. This is a Streamlit button. It might be a little difficult to see here on the projector, but yeah, it just says like submit. So you would then type st button and then put submit in the parentheses. And here we have text input fields. So these are just like a few examples, but there are endless opportunities with Streamlit. This whole thing as sidebars, you would put like st.sidebar, and for example, the text input like indented underneath the sidebar. And as Arnav went over, this is just a brief recap because it can be quite hard to get your head around. But basically, the user gives a prompt. For example, evaluate the potential of said startup. It then first goes to the researcher, and just remember that Tably is not an LLM. It's just a tool. We have an LLM in charge of each agent, but that agent specifically has Tably available as a tool. And then the two agents speaks with each other until they get a final answer, which then goes back to the user. So for creating agents, LangGraph already has this feature covered. It allows us to create something called React agents. And do not confuse this with React, the JavaScript framework for web development. This is just a term for agents specifically. It stands for reasoning and acting, which basically just means that the agent is able to reason about the task, create a plan, and then take actions based on that plan with the tools provided. And this lets the agent go beyond just generating text, like ChatGPT, for example. And for our app, we're going to be needing two agents, a researcher and an advisor. The researcher is going to be the one with the tablet tool, which will basically search the internet, gather market data relevant to our startup. This could be like market size, potential competitors, price structure, all these things that are relevant to a startup. And all the data that the researcher gathers will then be given back to the advisor, which will then make decisions like based on that research. And if the advisor deems that like the researcher hasn't gathered enough data, it can then like send a new prompt back to the researcher, which can then conduct more market research, and then back to the advisor again. So to get started, we have to initialize these models and tools. This is not the same as creating agents or anything. This is just kind of assigning our different models to a variable so that we can easily use them later. Don't worry too much about the syntax here. These are just some built-in like LangChain functions that lets us easily access these models. So for the LLM, we're using Gemini. With this model specifically, the Gemini 2.5 Flash. The reason we're using 2.5 Flash is because it's the best model that Google offers that has a free tier. And for Tably, we're just assigning the Tably tool here with this function called Tably search results. We're also limiting the max results to 5, just to avoid like way too long wait times while it does it research, as well as not like using way too many API tokens. Prompts. So this is the main way we kind of tell our agents how to do their tasks. So it's basically instructions to the agent. You can think of this as how you give instructions to ChatGPT. For example, you give them instruction like solve this math problem, but instead of giving instructions to like solve something specific, the prompts we're going to be giving to our models are more permanent and more personal. We're just kind of telling them like who they are. So yeah, you are a researcher, for example. In our program, we're going to be using two types of prompts. The first one is system prompts. System prompts are prompts that are relevant to all agents. So this is like general instructions. Let's say you have a team of like a software engineer and a product manager and a marketing manager. This would be an instruction you give to all of them. So yeah, basically, for example, user provided tools, you're in a team, collaborate with the other agents, as well as a stopping mechanism in our case. So we just want, for example, here we have prefix final answer with final answer. It's just like a mechanism so we can detect that the agent is done with its workflow. Then we have agent-specific prompts. These are prompts that will be given to the specific agent. And as you remember, we have two agents. We have one researcher and one advisor. So to the research, we would tell them, tell it like, okay, you're a research assistant helping evaluate startup ideas, but do not make any conclusions, for example. And to the advisor, he would say like, base your assessment solely on the research data provided by your researcher colleague. And now that we have our standalone agents with their own prompts, we need a way for these agents to communicate with each other. Do you have any ideas on how we can do this? I'll give you guys a few hints. Any ideas? What does Smallberg teach in CS32? Sorry? Close. One more hint. Yes, linked lists.
Yeah, so to get our agents to communicate with each other, we want to create kind of like a linked list kind of structure, which I'm sure some of you have heard of before. So in a linked list, you'll have multiple nodes, and each node is connected with each other through pointers. But we don't want something as simple. I mean, we could have something as simple as a linked list for our agent communication process, but we can also go way more complex. If we have multiple agents and multiple agents need to communicate with other agents, we can have something called a graph. And then in our case, it's going to be specifically a directed graph. And all that means that each node, like A, B, C, D, E, F, has a arrow pointing to another node. So that's just what a directed graph is. You can kind of think of this as a more complex linked list. So if you see at the top, the linked list, it just has one node pointing to another node, but the graph can have one node pointing to multiple nodes, and it can even have cycles, whereas the singly linked list at the top doesn't have any cycles. So yeah, that's just the basic structure. And then just if you haven't heard of a graph before, vertices are the circles like A, B, C, D, E, F, and then edges are just the pointers between the circles. So the arrows from like A to B, C. So we're going to be implementing our agent communication through a graph, because if we have multiple agents, we can easily just link them together by creating a graph structure. LangGraph makes this super easy to do. It's only a few lines of code, and you don't actually have to worry about any of the real implementation behind the graph. Okay, so for our startup advisor app that we're talking about, as we said before, we need two nodes. We need one for a researcher agent, and we need one for an advisor agent, and then we'll finally get to connecting these nodes to make a graph. And then once we have that graph, we can run our graph pipeline and then get our final answer. So first, we need a way to define a start and link our nodes. So if you see on the right there, that's kind of how we're going to link our nodes. We're going to have a start node, and then we're going to immediately go to the researcher to conduct research on a startup idea. And then we're going to go back and forth with the advisor until they have a final answer. And then finally, we'll return n to kind of return the final result back to the user. So it's a pretty simple graph for this demo, but again, you can have multiple agents with multiple tools. You can just imagine a bunch of those vertices on the screen with a bunch of edges connecting them. So yeah, and the way we're going to keep our information between these agents is something called messages state, which is provided by LangGraph, and it manages messaging passing workflows like our graph, and it also allows us to like maintain the state of our messages. So once I go to researcher advisor, I'll know the advisor will be able to know what researcher has said before through messages state, because that's how we store our agents' past responses. And then we'll walk through all this in the code demo later as well. So as I said before, LangGraph makes it super simple to start a graph. You don't have to worry about any of the actual implementation. So we're just initializing our workflow state graph with messages state. As I said before, messages state is just a way to store the state of the messages between your different agents. And then we're adding a node researcher. And then we're also adding our second node startup advisor. And then we want to know where to go to when we call start on our graph, right? So we're going to add an edge. As I said, an edge is just the pointer between the two nodes. And then we add our start edge because we want to start at the researcher. So we start at the researcher bottom. And that's honestly pretty much it for our graph purposes. Like you don't have to worry too much more about the graph implementation. And then about stopping the graph, we kind of just briefly said that, yeah, the agents will communicate before, the agents will keep communicating until they determine an answer. But how do they actually determine an answer? So remember the system prompt where all of the agents have to follow the system prompt? we can configure it like this. It doesn't have to be exactly like this, but you can come up with your own prompts, whatever works best. But we found that this method works pretty well, and also the LangGraph documentation agrees that this method is pretty good. So if we just put in a system prompt, prefix your response with final answer so the team knows to stop, we can just go through all of our agent responses, and then we can detect the final answer, and we can just return that message and immediately stop, so we don't have to, we don't ever get stuck in an infinite loop of any sort.
So just a summary of how the structure works. We have our nodes, research node, advisor node, etc. So they all do their own. So like the research node does its own research, and then we kind of do a check, like, okay, does the response contain final answer, like in quotes? If it does, then we're done. If it doesn't, then we move on to the next node. And it's a very simple structure. That's basically just how it goes, all the way until it actually reaches its final answer, and then we stop. We have put like a limit in our code, like a recursion limit, because if you let it go forever, it might never reach a final answer. So it's important to just like set like a max limit, so you don't like end up using up all your API keys, or taking ages.
Okay, so as I said before, we want to start the graph, and LangGraph also makes it pretty easy. We just do graph.stream, and that just starts all the events in our graph. And then as Sebastian was saying earlier, we want to set a recursion limit. And first, actually, before that, we want to enter our prompt in that argument. So as you see here, the syntax is just we're a user, and then we have a user prompt. So my user prompt would be something like evaluate whether a startup for providing penguin food for Hawaiian residents is a good idea. So yeah, that would be our prompt. It's pretty simple, just our prompt for whatever we're evaluating. And then a recursion limit, as Sebastian was saying, is the max number of steps that the graph can execute. We want to keep a hard cap on this. 150 is honestly pretty high, but you can set it lower. And that's just like, if we do end up getting stuck in some sort of loop, we don't really consume all our API credits. Or if we're going too long, we don't also consuming all our API credits. And then after the graph is finished running, so after graph.stream is finished going through the entire agent workflow, the events will contain the events data of the events variable right here will contain actions from our workflow. So for example, if we went from researcher to advisor to researcher to advisor, it'll have all those elements stored in it, so we can parse through them and figure out which one was our final answer. Okay, so that's kind of what I was saying before. Once the graph is started using .stream, it emits a sequence of events. Each event is a step taken by an agent, so researcher and advisor, going back and forth. We're looping, at the end, we're going to loop through each event. We're going to extract the message and check which agent responded with the final answer and store the result. And then when done, we're going to have a variable called data, which will contain the information from the last agent. So if you look at that little code snippet, we're just going through every single event in the events object. And then we're going to extract whether it was from our startup advisor or from our researcher. And when we're done with all the events, the data object will have the event for the last agent that was ever. Okay, so now if you from the slide before, data has the message from the last agent that was run, and we're going to extract the final answer from this object. So this may seem like, if you don't understand what this is doing, like straight off the bat, it's okay. But for example, each data object has a attribute called messages, and all we're doing is we're going to the data object, extracting that messages attribute, and going to the last message in our messages attribute. And in Python, you can just do that by doing -1. And then we're taking that message, and then we're just removing white space from it. So we have a clean final answer. So if you remember, data had the very last agent response. We're taking the message attribute from that last agent response, and we're getting the last message, which contains the final answer. We're removing the white space from that, last message, and then that becomes our final answer. So that little line of code is doing all of that processing. So it's kind of cool. Don't worry if you're confused. You can go back to these slides and they'll explain them, or you can just we'll explain it later in our like code walkthrough later as well. So if you didn't really get any of that, just know that final answer has the final answer of our graph pipeline. Okay, and now we're going to move on to the code walkthrough. So actually, okay, yeah, so we have a final answer right here. So this is the subscription service for penguin food in Hawaii residents. So based on the search results, there are no wild penguins in Hawaii. The only penguins mentioned are captivity, like zoos, and then these institutions. Therefore, subscription service for penguin food for Hawaiian residents would not have a market, so we wouldn't pursue that. Okay, so I'm gonna move on to the code walkthrough now. Please zoom in a little bit so you're able to see. Okay, this is fine. So this is just some of the libraries that we're gonna have to. This is all on GitHub too, so if you don't want to look up here, you can pull in the repository or just go on the GitHub and follow along. So these are all the libraries that we've mentioned that we're going to use. So I'll start off with Streamlit at the top. So Streamlit was just, as Sebastian was saying, the very simple library that can create web applications with minimal code. So I don't know if any of you have tried to make like a giant web app using like React or some other framework like Next.js, but usually they're multiple files, multiple lines, all that. But if you notice, our Python file is only like 150 lines long, and half of it is not even Streamlit code. And then we already have a simple web UI like this. And all we had to do was run our Python file. So it makes it super easy for creating web frameworks for testing like this. And then we're going to have our LangChain Google Generative AI. It's the same thing that you guys saw from the previous presentation. This is just how we get our model. And then we're going to include our tool, which is tabulate search results. And then to create our actual agents, so we're going to import create React agent, which is the reasoning and action agent that LangGraph provides to create our agents. We're going to include some objects called base message and human message. You'll see these later on in the code, but pretty much to summarize, a base message is like a base class for all the messages that we send, and a human message is a specific type of base message that pretty much tells a language model that I'm a human. So we can kind of, I don't want to say trick, but like we can kind of like control the flow of our agents talking to each other, where each agent thinks the other agent is a human, and we can get a response like that. And then we just have some other things like command and literal. These are just for function annotations. So if you don't know what a function annotation is, it's here's a good example. Like we're just defining what this function will return. So our research node will return a command that's a startup advisor. So that's pretty much what command means. It's nothing too important. And then finally, at the end, if you see, this is the messages state and then the graph model that Sebastian was also talking about. Messages state is simply how we maintain conversation history, and the state graph is the actual graph workflow that we're going to be using. Okay, so if you remember from the slides, we had like the st.title, st.write, like st.sidebar, that one like Streamlit summary. So that's pretty much what this is. We're just defining a simple UI so we know everything. We defined a sidebar for API key, and then our sidebar for our Tably tool key, API key, and then we're just assigning these values to our environment variables. If you remember from Kian and Lorelei's presentation about what environment variables were. So we're just assigning them so we can actually make API calls in our code. And then we also had this in our slides. Once we have all our API keys loaded in, we're just initializing our search tool, and we're also initializing our large language model, so Gemini. And then moving on, if you guys remember, system prompts and agent prompts, like the system prompt was the prompt to control all the agents, like the overall prompt, and then we have specific agent prompts for each agent, right? So we want to define a system prompt. So as you see, it doesn't have to be too long, but it just has to be pretty specific. So will be like, if you're able to if you're unable to fully answer, that's okay. Another agent will assist with different tools. Where you left off, execute what you can, and make as much progress as you can. So pretty much all agents will abide by this prompt. And then we have a little suffix attribute here. So if you're a specific agent, you can take the system prompt and then you can append your individual prompt to the end of this and to make a kind of general prompt for your agent needs. So for example, we have a research agent, and then its prompt is like, you're a research agent helping evaluate startup ideas. Your job is to gather relevant market data, consumer trends, blah, 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 like all these insights. And when we actually call our agent, we're just going to take all this text and then we're just going to slap it in the suffix field right here. So then we have a system prompt followed by our actual agent prompt. And then the agent will be able to work that way. And then similarly, we also have our advisor agent, which takes the research data and makes startup decisions. So yeah, it's same kind of thing here. We just take this agent prompt, we shove it in the suffix for the system prompt, and then we're left with a giant prompt that this agent will be able to follow. And then this is our stopping mechanism. So get next node. So we can see that we're passing in our last message as a base message, which is just the base class for all the message structures from our graph. If we have a final answer in our last message, we can just return the end command. If we don't have a final answer, we can return goto. And then as you see down here, goto will, depending on what node I'm in. So if I'm a research node, I want to go to the startup advisor. And then if I'm a startup node, as you'll see down there, I'll scroll more. But if I'm a startup node, I would want to go to a research. So if we have a final answer, we return the final answer, or else we just go to the next agent and keep continuing our cycle. So then moving on, this is a lot of code, I know, but I'm just kind of briefly skimming over to it. It might be hard to follow along if you're trying to follow along, but I would say like it's better to go back and kind of figure out what each thing is doing on your own time. Everything is commented and it explains every single thing what each line does. It's just kind of hard to type out like 100 lines of code in like an hour. So I'm just like briefly explaining what each stuff does. So when you go back and look yourself, you'll be like, oh yeah, I know what this does. So, okay, the next thing is we want to actually define our nodes, like we said before. So we have a research node and an advisor node. The research node, as you see here, will always return an advisor, a startup advisor, to conduct advice. Or if we have a final answer, it will return end. Same thing down here with the advisor node. It will always go back to the research node, or it'll just end if we have a final answer. That's all that's doing. It's just typing the function. Okay, so we want to call the research agent that we defined before with our prompts, if you remember from up there. And then we want to get our result. And then we want to pretty much determine which node to get to based on the content of the last messages. So if you remember this function up here, the get next node, that's our stopping mechanism. So we're just checking if the message from this node has the final answer in it. If it does have the final answer, we're just going to go to end and then immediately return. And then we want to, okay, yeah. And then we want to rename the author of the last message to researcher by wrapping it in a new human message. So once we're done with our output from research node, we want to send this output to the startup advisor if we're not ending, right? And we want to take this message from the research node and wrap it in a human message. So we're pretty much pretending that our research node was typed by a human, and we're giving it to our advisor node. So now the advisor thinks a human is asking it to do something, and it'll do whatever it's tasked to do with its prompt. That's all we're doing. We're just wrapping the message in the human message, and then we're going to send it off to the advisor node, which will be this command block right here. And it's literally the same thing for the advisor node, but inverse of what the research node is, because we're either going to the researcher or we're ending. We're again wrapping it in the human message, and then we're just going to the next node here. And then we're also checking if we have final answer with our stopping mechanism function over here. And if you remember from the slides, now we have all our nodes set up and we have all our prompts set up. And all we need to do is link them together through LangGraph. So if you remember, it's just these 4 lines right here. We start our graph and we initialize it with messages state to keep the conversation history. We add our researcher node, we add our startup advisor node, and then we add a start vertice, and we just connect it to that. We just connect that to our researcher. So as soon as we start, we're going to start doing research, and then the research will go to the advisor, and then the advisor will go back to the researcher, and then you'll get a flow like that. So we're compiling our graph, and there we go. Now this graph object has our entire graph in it, so it's just these lines of code. So once you've already set up your nodes, it's pretty simple. That's all you have to do, really. Okay, and now we're gonna actually run our graph. So we just have a Streamlit button called submit that was set up at the top. So if submit gets clicked, we're going to start processing the request. And this function call right here, graph.stream, this is also on the slide if you remember. We're going to feed in the user prompt, and how we get the user prompt is through a Streamlit text field that was also defined at the top. So we're going to feed this user prompt into our graph, and then it's going to immediately go to the researcher, as we define start as researcher. So that prompt will go to our graph. We're going to set our max number of switches to 150. And yeah, and then after all this is running, by line 160, once everything above that is done running, we'll have all the events in the final answer in the events object. So now we're going to go through every single event, like this is also on the slides, and we're going to get the data for each event at that node. And then at the end, at the final event in events, our data object will have the last agent that was ever run by our workflow. So now data will have the last event in our entire graph pipeline. And just in case some error happened and we don't have data, we don't have to check it. But if we do have data, if there was a final message, this is also one of the last slides. We'll take the last message, which is done by -1 in Python, and then we'll remove all the white space from it with content.strip, all the trailing and leading white space. And then we will create a Streamlit subheader called final answer. And then Markdown is just another way for Streamlit to kind of embed and display Markdown text, which is just a way of displaying text. It's just a text formatting format. So we'll take our final answer and then we'll format it with Markdown through Streamlit, and then we'll display it. If we don't have a final answer for some reason, maybe something went wrong, we'll just say no final answer was provided. And you don't have to worry too much about this. I'll show you exactly what this does in a second. But this is just the flow of our response. It'll display it. So if I go back, I actually have a picture of another prompt that which I tried earlier. So it was a startup idea for a subscription. Let me zoom in real quick. It was a subscription service for stinky socks with bowls. So as you can see, some of the research that our Tavily search agent did was that it used the internet to research market growth, and it came up with a lot of metrics like compounded annual returns, and then it even came up with a lot of data from the market, like the respective market for stocks from 2024. It kind of explains some of the, like right here, some of the maybe influences behind this growth. And then it says, it kind of like roasts our idea, and it says like the proposed offering of stinky stocks with bowls directly contradicts with consumer preferences. And then it says like, with the competitive landscape, do not pursue this startup idea. And yeah, and it gives like a brief summary of the justification later. And you can see remember I was saying like, you don't really have to worry about what this does. This is just a display feature that we coded in so you can see the flow of the response. So it first went to the researcher agent, then it went to the advisor agent, then it went to the researcher agent, and then it did some more research, and the advisor came up with another idea, and then the researcher, and then went back to the researcher, and then finally the advisor agent was like, okay, I'm done. I think I have a final answer. I'm going to give this back to the user. Yeah, so that's pretty much it for how to create a simple workflow. So that was the walkthrough pretty much. Let me know if you have any questions. I know that was a lot of code. Everything is once again just commented explaining what everything does. You can also go back in the slides or ask me. So now once you've done all that, you've built a fully functioning multi-agent network. You can either use this as a skeleton, copy it, change the prompts, do whatever you want. It doesn't have to be a startup idea. You can do something you can do literally whatever you want with it. You can make the agents search whatever you want. And then also, if you want to try other tools rather than just web search, you can go to that link over there, which is also in the slides, and you can do a bunch of cool stuff. Like I know there's like a Gmail one where you can automate your email messages. Like if you don't feel like replying to your emails, you can just make LangGraph do it for you instead. But yeah, there's a lot of cool tools, so you should check that out. Or you can just use the template that we gave you and do web search. But yeah, that's pretty much it.
Yeah, and just as Arnav said, where's the yeah, if you want to like implement like any other models or tools, it's very, very easy. Let's say you want to use like OpenAI instead of Gemini. You literally import I remember the exact syntax. It would be something like import chat OpenAI instead, for example. And then when you like assign your models down here, you use OpenAI instead. You can even use both if you want. Let's say you want one agent to use Gemini and one agent to use OpenAI. You can do that as well. If you want any other tools, for example, for doing medical research, you can very easily add that as well. You can create more agents. You can have like a triple agent network, for example, or give multiple tools to one agent. So like the possibilities here are basically endless. So yeah, that's what we have.
So that's all implemented under so if you remember I was talking about like messages state and LangGraph, that's how the conversation history between the agents is tracked. So we don't actually have to worry about that because that's what LangGraph has done for us. Through messages state, it'll take the output like from the previous agent, right? And then the new agent will get this previous output, and then it'll do all its LLM stuff, do its research or make its advising decision. And um we have to configure the prompts in a way that allows this. So for example, like in my system prompt, you see here that says, if you're unable to fully answer, that's okay. Another assistant with 2 different tools will help you where you left off. So it's a combination of the prompt being configured the right way, because if you don't include this in the prompt, yeah, what you said is going to happen all the time. Like it's going to go to one agent and it's going to immediately return. But if you just ask the agents to be like, I guess like very, I don't know what's the word for it, be like conservative in what they do, they will be conservative, and many times that you'll see like long pipelines of flow that you see it. So it's mainly a prompt thing, and then it'll be passed through messages state, and then so it's mainly a prompt thing to answer your question.
Yeah, and also like so like Tablet does like a huge amount of research at once because that would take like a lot of time and a lot of API credits. So if you see here, we set the max results to 5, just to limit it a bit. If you don't put like a max results, it might do like way more research, but like everything might not be as useful. So yeah, it kind of limits the tool to like not do too much research at once as well. Any other questions?
Yeah, good luck guys in building your multi-agent frameworks.
So the main takeaway from this, I'm gonna end this recording.